So this is day 8. And what we're going to learn today is we're going to learn how to identify the instantaneous rate of change of a function. We're going to start off with the slope formula, and all we're going to do over the next probably 5 or 7 minutes is manipulate the slope formula into different forms. Here's what we're going to start with. We're going to say we know that the slope of any function is equal to y2 minus y1 over x2 minus x1, right? So if you take any 2 points, if you take the point x1, excuse me, I meant to be right now, there we go, x1, y1, and then another point x2, y2, right? That you can plug these 2 points into this formula and get the rate of change between those 2 points. And it will be a linear, a straight line slope, right? Meaning you could create the equation of a straight line between 2 points, okay? Now, so this is our slope formula. And you've been using this since you were probably in 7th grade.
Yeah.
Does that sound about right?
That sounds about right.
Okay, maybe 8th grade, maybe 6th grade, I don't know. Okay, so now, the other day, we took this a little bit further. Here's what we said. We said that as you continue in your math education, you begin to learn that the letter y can also be written as f of x, right? This is using function notation, right? Yeah. And that when we do this, we now have to, instead of using x1 and x2, we're going to represent x1 as the letter A and x2 as the letter B, right? So we are indicating that we have an interval, an x interval that starts at A and ends at B, correct?
Yes.
And that when we do this, slope is now in the formula, okay, where at the bottom, instead of having x2 minus x1, we have b minus a. Now, in the numerator, y2 is an output that goes with x2, right?
Yes.
And x2 is the letter b now, right? Okay? And therefore, the output, instead of being y, is now an f, so the output would actually be f of b. We're plugging b into the function, right? Okay, so y2 is the output that goes with x2, correct? So y2, x2 leads to y2, correct? But now, since we're using instead of saying y, we're saying f of x, it would be f of b because our input is b. So the input b leads to the output f of b. And the input a, the other x, that's x1, is going to lead to the output f of a, correct? Are we okay with this? All right, and if I were to write these as coordinates, they would be b, comma, f of b, and a, comma, f of a. Right? This is the same thing as x2 and y2 and x1 and y1, right? It's just another way to write the same thing. But we're writing it in function notation instead of x and y notation. But it's still the same thing. Okay? And so, instead of y2 up here, we would have f of b minus, instead of y1, we would have f of a. So this is still the slope formula. It's still a y that goes with an x, a y minus another y, and the other y goes with an x. So a y minus a y divided by an x minus an x. Are we okay with that? All right, good. Now, if you can understand that, then we can take this more steps further, okay? I'll leave this over here just for now, but eventually I'm going to have to erase it. So now, our slope formula is now f of b minus f of a over b minus a, right? And you use this to find the average rate of change of functions, correct? Okay? All right. So if we had the function f of x is equal to x squared, and we wanted to know the average rate of change between 4 and 7, right? Then we would just put in the average rate of change would be a slope of a line that connects 2 points. What 2 points? Well, 4, what is the output that goes with 4 from f of x? What is f of 4? 16, right? Because 4 squared is 16, okay? And then if we plug 7 in, what's the output? 7 squared is 49, right? So the slope of a line that connects these 2 points. Now, this is a parabola. It's not a straight line. Therefore, the straight line that connects these 2 points is not on this curve. It's a shortcut along the curve. So if you have this parabola, you have one of your points here, 416, and you have your other point here. It's kind of a straight line on the inside that connects the 2 points. It's a shortcut. Instead of going the long way around, you take a straight line. As we call the average rate of change the slope of the secant line. It's the slope of the secant line. Secant lines connect, or they touch, a curve in 2 places.
What do we call this secant line, the slope?
It's the average rate of change. So the average rate of change of a function is the slope of a secant line. And that is the average rate of change. Now, what I'm about to move you toward is we are going to understand all of this same stuff, but instead of average rate of change, we're going to understand it as instantaneous rate of change. Instead of finding the slope between 2 points, we are going to find the slope at 1 point. At an instant. Instead of over an interval, it will be at a single point. We won't have 2 points between. It won't be between 416 and 749. It will be the slope at 416 only. And because of that, the line will not be touching the curve in 2 places. It will be touching the curve in 1 place. Does anybody remember the name of a line that touches a curve in only 1 place? It's called a tangent line. So instead of finding the slope of a secant line, we will be finding the slope of a tangent line. Now, this is a problem. And the reason it is a problem is because normally every technique that we have used, every technique that you have used in your math life to find the slope of a line has relied on how many points? 2 points. So to find the slope of a line with only 1 point is kind of a magic trick. And I'm going to show you that magic trick today. This would be simply, if we wanted the average rate of change, we would put in, 49 minus 16 over 7 minus 4, which would be 33 over 3. So the slope would be 11, right? The average rate of change between these 2 points would be 11, okay? Sometimes we refer to this y2 minus y1 over x2 minus x1 as change, oops, that's an A. Delta y over delta x, right? Change in y over change in x. Delta y over delta x, good. So that means, can we agree that this is also delta y over delta x? Is that okay? But here's what I do want to call your attention to. Can we agree then that b minus a is delta x? That b minus a is equal to delta x, okay? And so what that means that we now have is, our slope formula is now f of b minus f of a over delta x. Do you see this delta x? Delta x is 2 characters, right? And if I cared a lot about space and I cared a lot about ink, I wouldn't want to have to write 2 characters, and if I cared about time. So what I want to do is I want to use a different letter that will always represent delta x. And that letter is the letter H. So instead of writing delta x, I'm going to write H. That means every time that I write an H, I mean delta x. So now I could write the slope formula as f of b minus f of a over h. If h is equal to b minus a. Right? Is this true? B minus a is equal to h? Is that okay? If this is true, then watch what I'm going to do here. I'm going to do some kind of funky, it's not funky algebra, it's just regular algebra, it's just tedious algebra. So I don't want you to get too confused. Excuse me, I'm going to add a to both sides. I'm going to add a here, and I'm going to add a here, which is going to give me a plus h is equal to b. So can we agree that b is equal to a plus h? This is important, okay? All right, now that we can agree that a is equal to, a plus h is equal to b, watch what I'm going to do now. I'm going to go back to this, to our slope formula. And so what we're now going to say is that slope is equal to f of a plus h minus f of a over h. We're almost there. And here's what I need you to remember. That this is a slope formula. This is still a slope formula. Okay, it is ugly, but it's actually, to me, it's beautiful. So, watch this. We have what? We still have 2 points. You're right, and that's okay. We're gonna. Right, we're getting there. We're getting there. It is still 2 points. Because here's the thing: if we go back to this problem right here, right? What is delta x? Nope. Hang on, that's 7 is b. What's delta x? 7 minus 4, which is 3, right? All right, here's what y'all need to understand, that delta x is the distance changes, the jumps in x. So how far did we jump from 4 to 7? 3. So the delta x is 3, correct? So if a is 4, then I would put a 4 here, right? And then over here, I would put 4 plus 3. And what's 4 plus 3? 7, right? And here, what would I put? 3, because h is delta x, right? So this is still f of 7 minus f of 4 over 3. It's still 49 minus 16 over 3. The answer is still 11. I'm proving to you that this is still this. See what I mean? I'm just manipulating it so that it looks different. Okay? I'm just using algebra so that it looks different.
Is this manipulation
right?
to get us to
Yes. Yes, it will. Yes. Okay, so now, if you're okay with this, I only want to make one more manipulation if you're okay. Okay? Here's what I want to do. Do we agree that A is an x value? Okay? If A is an x value, the reason we had A and B up here is because we had 2 different x values. But now that we only have one variable representing an x, can I just put an x in there instead of an A? Are you guys okay with that? So really, our slope formula now, and this is what you want to write down, our slope formula is f of x plus h minus f of x over h. That's our slope formula. All right, now, and I'm going to write this up here. So our slope formula is now f of x plus h minus f of x over h, right? And let me show you now how we can use this. If we say, and we know that h is delta x, okay? H is delta x. That just means the change in x. So now I don't have to say what is the slope, what is the average rate of change of x squared from 4 to 7. I can say, what is the average rate of change of f of x, where x is equal to 4, and where delta x, which I would say h, and where h is equal to 3. And now we just plug in. So I would put what would I put here? 4 plus 3 is 7, right? So the slope would be f of 7 minus f of 4. Guys, I know Octavia isn't the only person in the room. Over 3, right? And then f of 7 is 49. F of 4 is 16 over 3, which would give me 11. Right? All I'm really doing here is teaching you a new formula for slope. I'm just teaching you a new formula for slope. To where now, instead of having to pick 2 points, you just have to pick 1 point and then identify the delta x. Now, here's a question for you. Let's say that I have some arbitrary curve on the coordinate plane, and the curve does this. Okay? Folks, I might try to go over here. Let's say that I want to know the slope of the curve at a single point, right? But I need 2 points. I need 2 points to find a slope. So let's say that I just pick some other point over here, right? And I have a secant line. And whatever the slope of that secant line is, I would call an approximation. An approximation of slope. It is approximately the slope of this curve at that point. And let's say that the x going from here to here, this is where I want to know. So this is my x, right? And I want to know the slope at that point. And let's say that my delta x, let's say that h is equal to 1. What can I do to improve my approximation? The concept is very similar to the idea of pixelation. Have you seen a high definition television before? Okay. Have you ever seen a television with lower resolution? Yes, yes. Okay. What's the difference in terms of the image?
One's clear and one's not.
One of them's clearer, right? Now both of them are not perfect. That's correct. The pixels are smaller. When you make the pixels smaller, the image is clearer. It's more like the real thing. Now, no TV ever will have the resolution of standing in front of a person. This is real. Am I looking at pixels here? I am looking at skin. I am looking at atoms, right? I'm looking at clothing and hair. Am I looking at pixels? No. Am I looking at live? Am I looking at an approximation of what you look like?
No.
No, I am looking at you. But when I look at a screen, I'm looking at pixels.
An approximation.
Now, when I get a high definition television set, I can barely tell the difference, right? Because it's high definition. But if I took a photograph of you with a high definition digital camera and then zoomed in, what would I see?
Pixel.
I would see the pixels. Do you see what I'm saying? But when the pixels are smaller, I get a better approximation of the true image. Does that make sense?
Okay,
So that's what's happening here, is that when you decrease the delta x, you get a better approximation of the actual slope, right? So let's go over here. Right, so now look, let's say that we want to know the slope of x squared. Not between 4 and 7, but at 4. But we can't because we need 2 points. So we could use 4 and 5. Does that make sense? Couldn't we use between 4 and 5? I know it's not that small, but it's better than 4 and 7, right? So in this case, we're choosing x equals 4, and what is our delta x?
5 minus 1, yeah.
1, right? Our delta x is 1. And so now our slope is going to be f of 5 minus f of 4 over 1. 5 squared is 25. 4 squared is 16. 25 minus 16 is 9. 9 divided by 1 is 9. So we just, before the slope we had was 11, right? Now our slope is 9. 9 is a better approximation of the slope at 4 than 11 was. So now, look, I want a better approximation. So what do I do to my delta x? Make it smaller. Let's make it 0.5.
Wait, so we aren't changing, we're still changing x2, right?
Correct. We're only changing x2 because we're sticking with this x1 is still 4. We are trying to zone in on the slope at 4. Okay? So now watch. Now, instead of it being f of 5, it's now f of 4.5. I need somebody to look up 4.5 squared, please. 20.25? All right. Over 0.5. So now, 20.25 minus 16 is going to be 4.25 divided by 0.5. 8.5. Something doesn't seem right about... Oh, that's right. Yeah, that's right. It's times 2. Wasn't thinking. My math broke in my head. What's that? No, because we went from 11. Here's what we did. When the other point was 7, look at this. When the other point was 7, the slope, okay? Sorry, let's do this. Sorry. When the change in x was 3, the slope was 11. When the change in x was 1, the slope was 9. Now the change in x is 0.5, and the slope is 8.5. 0.25. Let's make delta x 0.25, shall we? Actually, why don't we just cut to the chase? Why don't we go to 0.1? Is that okay? Let's make our delta x 0.1. All right, that's right. Let's cut to the chase. So now our delta x is 0.1, and so now we have f of 4.1 minus f of 4. I need to know what 4.1 squared is. And we're going to make and then down here we're going to have 0.1. 16.81. Is everybody okay with that? Okay. All right. And then 16. So now what we're going to have is 16.81 minus 16 is 0.81 divided by 0.1. 8.1. So now when our delta x is 0.1, our slope is 8.1. What is this approaching? No. This is approaching 8. What is delta x approaching? 0. Yes. Our delta x is approaching 0, and as our delta x approaches 0, our slope is approaching 8. Right? Does that sound familiar to you? Yes. Limits. What we really want is when the change in x is 0. Am I right? Isn't that what we really want? Do you want that? Isn't that where we're trying to go? If we don't want the rate of change between 2 points, we want the rate of change at 1 point. We want our delta x to actually be 0, right? Okay, so let's go ahead and plug it in then. What's 4 plus 0? 4. So f of 4 minus f of 4 over 0.
That's 0.
Correct. What is the numerator?
0.
So we have... Exactly. Which means what do we have to do to solve this problem? We need to use a limit to solve the problem.
I see how it's all tying together.
And so here's what we really want to do. Here's our formula, right? What we really want is the limit as h approaches 0 of f of x plus h minus f of x over h. That's what we really want.
That's kind of blind. Who made this up?
And this, I don't know, some smart math dude, you look that up on the internet And what it'll come up as is the limit definition of the derivative.